In today's class, we will see problems based on radioactivity, specifically half-life and isotope dilution. Before we begin the problems, radioactivity, as you all know, is the spontaneous emission of radiation in the form of particles or high-energy photons, which is alpha rays, beta rays or gamma rays from nuclei as a result of nuclear instability. So, the isotopes that exhibit the phenomena of radioactivity are called as radioisotopes. You already know isotopes means they have the same atomic number, but they have different atomic mass. So, isotopes which are unstable and which exhibit radioactivity are called radioisotopes. Some examples of radioisotopes are H3 tritium, P32, C14, I131, etc. We'll move on to the problems. So, mainly three terms we have to remember when we are talking about the life of radioactive element. One is called as half-life, it is denoted as T half. The other is denoted as K, which is called as decay constant or disintegration constant, and you have another term which is average life. Half-life is the time taken by the radioisotope to reduce to 1/2 of its original concentration. So, it is given by the formula 0.693 by K. So, K will be 0.693 by T half. So, the average life is the average lifetime of all nuclei of a particular unstable atomic species. Please ignore this T. Here this is actually equal to 1 by K. You can remember it as 1 by K. That means you have to take the reciprocal of K. So, K is 0.693 by T half, means average life will be T half by 0.693. So, this is how you can remember it. Now, we will see problems based on this. Calculate the half-life of I131. The decay constant is 0.0866 per day. So, if they have given the units per day, our result also will be in days. If it is minutes, it will be minutes. If it is years, it will be years. Because this is having no dimension, this is having no unit. So, T half is 0.693 by K. So, 0.693 by 0.0866, which is 8 days. Now, here we calculated half-life. Next, we can calculate what is K. So, calculate the decay constant of P32. They have given the half-life. Half-life is 14 days. So, K will be 0.693 by T half, 0.693 by 14, which is 0.0495 per day. Because they have given days, our unit will become per day. Now, they have asked additional calculation of average life in this problem. So, half-life of radium is 1580 years. Calculate disintegration constant and average life. So, K is 0.693 by T half, 0.693 by 1580. So, you get it because it's given in years, you get it as per year. So, average life will be the reverse, T half by 0.693, which is 2280 years. Now, if they ask us about what is the amount of radioactive substance remaining after a particular time, this is the initial concentration, then we can use the formula A is equal to A naught into half power T by H. So, A naught is the initial amount of the substance with which we begin. A is the substance remaining after a time T. So, that time T is given by T, and instead of putting T half, here we are putting it as half, which is the half-life, okay, just for simplicity's sake. So, you can find out A when they give these values, and you can also find H or T, half-life or the time taken. For example, they can ask a question, this is decaying to so much amount, only after a particular time so much is remaining. So, they have given the time, what is the half-life? Or they can give the half-life and they can tell that from 100% now only 20% is remaining. What is the time taken for it to decay? So, we can find even T. So, you can find A, you can find T, you can find H. So, we will see the problems based on that. So, the first problem is they are going to ask the remaining substance. So, simple problems. So, the half-life of zinc is 71. Is 22.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has expired? Remember, the units should always be the same, otherwise we should convert the units and make it same. So A, so initially how much is there? 100 is there. So they are now asking us what is going to remain. So initially 100 is there. So 1 by 2 we can put it as 0.5. So what is the time they have given for us? 7.2. And what is the half-life mentioned in the question? It is 2.4. So 100 into 0.5 power 3, 100 into 0.125, which is 12.5 grams. This is very, very simple to work out. Same way we'll see another problem. Not. So here palladium has a half-life of 3.6 days and we began with 6.023 into 10 power 23 atoms. So how many atoms would be present after 20 days, they have asked. So A is equal to A naught into half power T by H. This is the initial amount, 6.023 into 10 power 23 into 0.5, and 20 days is the time given, 3.6 is the half-life. So 6.023 into 10 power 23 into 0.5 power 5.55. So if you solve this, you get this. After multiplying, this is your answer. So this is very, very simple for us to find the remaining amount. If we want, they can ask us to find A naught also, initial concentration. Next, we will see one example for how to find out H and one example for how to find out T. So this is little bit different. After 24 days, 2 milligrams of an original 128 mg sample remains. What is the half-life? So they have not given the half-life. So A is equal to A naught into 0.5. 1 by 2 we are putting it as 0.5 T by H. So initial amount is 128. Amount left is 2. 0.5 power 24 by H. We have to find out 24 by H. So you first remove this number here. So this will become 2 by 128. To solve, simplicity for us to solve, that's all. So 2 by 128 is equal to 0.5 power 24 by H. So whenever we have an exponential form, when we want to solve it, we have to take log on both sides. So log 2 by 128 will be a log of H, which can be written as 24 by H log 0.5, because there is a formula, log A power B is equal to B log A. So this exponent will come before the log. So 0.5 power 24 by H, which we can rewrite as 24 by H log 0.5. Now the log of this, first we have to solve this. So this is 0.015. So log 0.015 is equal to 24 by H log 5. Log 5 is 0.301 and this is the other log. So both are getting cancelled. From this, H will be equal to 24 into 0.301 divided by 182, which is equal to 4 days. So for solving this alone, you have to take log and you have to do it. But for finding out the remaining substance, it was very, very easy. We didn't have to go to log. Similarly, to find out T also, we have to take log. We will go to one question on that. Similar way of doing it. And here they have asked the time T for us to find out. And whenever we use the radioactive carbon to find the age of fossils, it's called as radiocarbon dating. So it can tell how early a particular fossil has been buried. That also we can find out. So A is equal to A naught into half power T by H. I told you they can give in any units. So here they have given it as percentage. So whenever they give it as percentage, remember you have to put the initial concentration as 100, 0.5 T by 5770. As usual, you have to bring this number here and then you have to take log on both sides. So I've already divided it and put it as 0.3332. Then T by 5770 log 0.5. I've already explained this to you. So again the two negative terms, minus sign gets struck off, and then you will have T will be equal to 0.477 into 5770 by 0.3010. So the age is, it has been buried 9143 years ago. So these are the problems which are based on half-life. We will now move to a concept called as isotope dilution. This is one of the applications of radioisotopes. So here what happens, it is a radiochemical method of analysis for measuring the amount of a particular substance. See, suppose we have a particular element or a particular compound which is present in a sample, but it is, we don't know, we want to estimate the amount. So what we can do is, we can take the radioisotope of the same element or radioactively labeled compound, and what you can do is you can measure the initial specific activity. Specific activity means activity per weight is called as specific activity. Just like, so you will measure it initially and then you will mix it with this compound. When you mix it with this compound, the isotope will get diluted and so its specific activity will decrease because you have the same element extra which was already present in the solution. So what happens? Specific radioactivity gets decreased, and based on that we will be able to find out the amount of the substance that was originally present. So that is why it is called as isotope dilution. So this is the formula. X is equal to A into S1 by S2 minus 1, where X is the amount which we want to determine, some element or some compound which we want to determine. A is the amount of radioactive element or radio-labeled compound that is added. S1 is the initial radioactivity, specific radioactivity of the radioisotopes before mixing. S2 is the specific radioactivity after mixing it with the compound to be determined. So this will always be less. So this is minus 1. So you can solve this and subtract 1 from it. So same thing, another example here, 5.2 mg of C14 labeled leucine with specific activity 511 is added to a sample of leucine. This concentration only we want to determine. The resultant material had specific activity 86.96. Determine the amount of leucine in the sample. So initially we are starting with 5.2 which we are going to add radioactive material. 511 is the initial specific radioactivity, 86.96 is after mixing. When you solve this, you will get 25.41.